I just realized I accidentally used the NERSC theme for this intro slide. I apologize. We're not all NERSC branded. So I guess two of us are, yeah. So we just wanted to say hi. Welcome to the Julia for HPC tutorial. I don't know if folks wanted to say anything. I just wanted to introduce the great speakers that we have. So I will introduce myself in a second, and then Sam Omlin from CSCS has come here from Switzerland to talk about GPUs. So thank you very much.
Yeah, I will talk about like performance-driven GPU programming with a particular approach from 11 to midday break and then after midday break.
And Raye Kimmerer, which is well known in the Julia community, will be giving us a little bit of an introduction to multi-threading and then of course performance portable programming as well. So did I cover everything?
I think so. Yeah, yes. I'm at NERSC right now. This summer I'll be at Princeton in the fall. I'll do a bit of sort of CPU parallelism, not too much. I think we'll focus a lot on GPUs, and then I'll do also a little brief introduction on sort of what GPUs look like before Sam takes over on the real meat of the GPU programming.
And I have the unenviable task of talking about MPI, which I think is maybe the worst feature of HPC, but unfortunately we have to address that too. So anyway, and we will also be joined soon by colleagues from PSC, Pittsburgh Supercomputing Center, who got, I think, stuck in traffic or something like that, but they will be here soon. And anyway, yeah, so, yeah. Oh, sorry, yes, you should have got, I am so sorry. Yeah, we also have, in fact, this is maybe a good time to throw up the folks that are helping with this. So
This is Ranjan. He's co-executive chair of the conference with me, and he works at Julia Hub, and he'll be introducing sort of the Julia Hub platform for sort of single node work, and also a little bit on multi-machine work on Julia Hub. So yeah.
And so speaking of machines, I will. So for folks who have signed up for NERSC and PSC accounts, I will be managing those accounts. So during the tutorial and also during JuliaCon, you can then use, for example, NERSC Perlmutter or PSC Bridges 2 or Julia Hub. And so Julia Hub have donated credits so folks can experiment with cloud computing in Julia as well. And if there are any questions, please raise your hand at any time. If it's like something boring and bureaucratic, like why does my account work, we don't have to add it to the record. But if it's a technical question, we have a mic, and so I would kindly ask folks to address your questions into the mic to make sure that the folks that will watch a recording can actually know what's being asked. All right, so yeah, thank you to the great speakers, and so I think I'm just going to get started with some introductory remarks, and at any time, please do ask. We have lots of, it's a whole day tutorial. The idea is we don't want to rush things, and so, so to get access to Julia Hub credits, you can just scan the QR code above, or use this. What is it? This code here. I'm sorry. I'm gonna move my mic a little bit because otherwise I. So, anyway, so we'll flash this up again later if, well, I'm seeing smartphones out, so I'm waiting for people to take a snapshot. All right. Nope, still being recorded. All right, I think everyone's got their code. All right, and so in addition to the Julia Hub, maybe I'll put the Julia Hub credits in the GitHub as well, and so that way you can get access to that too. So I want to maybe start and point out to the interactive materials. This is sort of a kind of a Franken repo that keeps growing and getting interesting things added to it. So please feel free to explore, but we'll also be using some of these in the tutorial, and some folks have prepared external materials, and I will link that to this GitHub repo so that folks can have can revisit tutorial materials. And just to orient folks, so right now we're in the morning session, and so we'll be spending, oops, I left, so some of this is for planning, so I've left maybe like an hour to get like intro work done, and then we're going to get down into the guts of Julia. There's also coffee breaks and then a lunch break to keep us all sane. So this is the morning session. We'll be covering single node parallelization and the basics of GPU programming, and then in the afternoon we'll be doing more advanced GPU programming, and then you know, how to go from single to multiple nodes on HPC systems, and then we do performance portable HPC, which I think is near and dear to a lot of people's hearts because, you know, many data centers have different architectures. All right. And so I want to also put frame the context of HPC, especially newcomers to HPC, in this video here. This is, I think, a metaphor for many things in the HPC world. But in this case, I would like just to make you not feel bad if things aren't going right. So HPC users are like the little ducklings, and the mama duck up on top of the stairs, that's maybe an HPC veteran or maybe a vendor or whatever. But the point is, you know, for the mama duck, it was obvious to get up these stairs, and now all the poor users have to like somehow manage. And you can see most of the time we try and we fail. Sometimes people get are lucky and get to the top quickly. But the point is, please try again. Don't give up. You can see the ducks are slowly progressing up these stairs. And once you're at the top of the stairs, you know, it's great. Yeah. So, if it lets me. All right. So I'm trying to advance the slides, but it won't let me. Oh, yeah, it's because this deck is done. All right, so if we just go now into the intro part of the tutorial. Oops, you know, I like animal videos. All right, wrong button. I'm sorry. So, I realized I didn't actually introduce myself. I'm Johannes Blaschke. I'm a workload performance specialist at NERSC. And actually a lot of the compute resources for this tutorial are at NERSC. So if folks have signed up ahead of time and you've gotten yourself a NERSC account, then I wanted to give you an introduction to our HPC systems. First, some broader context why we're even doing these sort of things. So in case you haven't heard about the US Department of Energy, it's also sometimes jokingly referred to as the Department of Everything, because we do a lot of things that aren't immediately obviously about energy. For one example, we are one of the largest funders of physical science research in the world and in the US. The work we do pretty much covers every scientific discipline. So that means, when I say users, by the way, I mean scientists who are not working at NERSC, but working with NERSC. And so our users pretty much do every possible scientific research, and that also means that our workload reflects this. And so I just wanted to illustrate two things here. The first thing is this pie chart here represents the sort of overall breakdown of different research areas. And I realize now these are all these horrible acronyms, but basically think about basic science, fusion, high energy physics, biological and environmental research, computing science, nuclear physics, and collaborations with industry. These are all different things that we do. And in case you're thinking, oh, but that's not really my thing, I want to illustrate this, this second pie chart here. And like especially this green little wedge here, it might not look very big, but we do have a lot of compute available. So if you are a researcher at a US university or you are collaborating with US researchers and you would like to explore HPC resources, you can apply to the director's discretionary reserve to do explorational work at NERSC. So I recommend that if you are curious to actually apply for your own compute grant at NERSC. And so we've been around for 50 years now. It's kind of longer than I've been around. And we started with pretty much like the early Cray systems. It was kind of, you know, there's some old stuff in the lab. It's kind of fun to look at. But since then, we have expanded not just to be a compute center that supports fusion research, but any research globally. And we have, this slide is a little out of date actually, we have over 12,000 users, active users right now, distributed across over 1,000 projects at NERSC. Also, again, I want to illustrate, you know, if you think about US Department of Energy, you might think, you know, Stranger Things or other like things in pop culture, but we're not like that at all. Actually, most of our users are from universities. We do only open research, and if you actually add it up, the grad students, the postdocs, and where are we? And the undergrad students, you'd get to more than 50%. So most of our users, most of the work done on our data center is not done by the professors and by the senior PIs, but by early career scientists. So again, I want to encourage you to explore that further if you would like. I would be amiss to point out to fail to point out that a lot of our research is also very high in impact. So you will be using a system called Perlmutter. When I say Perlmutter, I mean the system, not the person. But also Saul Perlmutter is a real person. He's a Nobel laureate, and he actually used our earlier systems to conduct some of his Nobel-winning research, and that's why the machine Perlmutter was named after Saul Perlmutter. So yeah, we do a lot of high-impact research. And so that's kind of cool. The sort of starting to get to why we care about Julia. So if you think about HPC, quite frequently you sort of think about this side of the spectrum of what happens at a data center, right? You have like large monolithic applications, you know, they run on a significant fraction of the machine. And they're sort of one statically or like one tightly coupled setup, really. However, our workload is evolving. A lot of data centers are starting to realize at least that, you know, AI is a thing, and the way that AI interfaces with HPC is different to how traditional HPC systems are built. And also, and this is really near and dear to my heart. This sort of illustrates, is a sort of a cartoon of what we mean with real-time data analysis for experiments. So this building here, by the way, I just realized, yeah, so you can see my mouse. This building here is a particle accelerator at Berkeley Lab, and you can kind of imagine you have a beamline there with a detector, and so that's what's happening here. And so the beam hits a sample, so the beam hits a sample, that scattered light then hits a detector, and you might collect thousands of images or maybe millions of images a second, and so that's what this data set here is. And you want to know, are you using your sample correctly? Do you need to tweak your experiment? And you might need a supercomputer in the loop to tell you, hey, yeah, you're doing everything right, or maybe you should tweak something on your experiment. And for that, you can't just have, you know, data being sent to a supercomputer and then like a couple hours later it goes to the queue and actually analyzes the data. You want real-time feedback to use your experiment wisely. And so so this sort of is an illustration of how we are changing as a data center. So when I joined NERSC, it was like many mod sim and a bit of experiments, and now we're kind of imagining how we can kind of mush everything together in one big, tightly coupled but difficult to manage blob here. And what we're not going to cover in this tutorial is obviously at some point we have like quantum computing and other Gen AI and stuff like that in the loop. All right, so pretty much everyone from a data center likes to talk about their data center, and so unfortunately you have to endure that here as well. So if you're running jobs at NERSC, this is the setup that you will be using. So up here, this is the supercomputer. When it was deployed, it was number 6 on the top 500. Since then, I just checked this morning, it has slipped to number 25. And it has almost 100 petaflops of compute available. Now, if you just have a supercomputer, that's not really helpful at all, right? Like you need all sorts of other things to make it useful. And the first thing is obviously a file system. So you have the Scratch file system for high performance, but relatively low capacity. And that file system is connected directly to the computes. And then within the network of the data center, you have a bunch of other file systems. So your homes, what's called CFS, and the tape archive. And you can see all of these things have different bandwidths on the interlinks. So you can imagine if I want to run a very compute-intensive job, it would be kind of silly to run it out of home. You probably want to run it out of Scratch. And then, of course, you need to be able to wire this thing up to the rest of the world. And so that's where we then have a high availability, high bandwidth network provided via ESNet. And also, just very quickly, you might have not, actually this slide is out of date because this should be Doubtner, but we also have another system coming next, 2026? Yeah, delivery will start 2026 and it will be available, hopefully, if everything works, in 2027. So keep an eye out for that. All right, so if we were to zoom into the compute nodes, this is basically what you would see. Since I can't take you to the machine room, this CAD rendering will have to suffice, but you can kind of imagine a supercomputer is really like the same thing over and over and over. And so here we have a whole bunch of cabinets, and if we zoomed into a cabinet, each cabinet contains these blades here, and then you can kind of see a rendering of that. So if you're using the GPU nodes, there's two kinds of nodes available on Perlmutter. So that's why when you submit jobs, you can specify CPU or GPU nodes. So for the GPU nodes, you have 4 NVIDIA A100 GPUs. So those are these little blobs here, together with a AMD Milan CPU. And there's also 4 network interconnect cards corresponding one to each GPU. And then if you're submitting to CPU node, you get 2 AMD Milan CPUs, only 1 network interconnect, and no GPUs. And so this is just something for you to kind of visualize where things are running. I mentioned the layout. So yeah, as I said, like each GPU here corresponds to a network interconnect card. This might be a lot of information, so please feel free to ask questions. I just want also for folks to really get an idea of like these HPC systems. They can be very complex, and pretty much no HPC system is identical. And so I'm kind of giving you the background, and I'm happy to answer questions also in the break. But for the purposes of this tutorial, what I want you to take away with is that you have different kinds of nodes. They're optimized for different capabilities. You've got different kinds of file systems. And you have to be aware of where your traffic goes. So for example, if you're running on this GPU here, which is on the same NUMA domain as this network interconnect, then it would be kind of terrible if you started using the address of this network interconnect to send data, right? Because then you are adding additional hops here, and that will slow things down. All right, I mentioned file systems. This is really, really crucial in HPC. Depending on what data center you're working with, depending on what scales you're thinking about, this might be worse, or or maybe totally manageable. At NERSC, it's been a constant pain point because of the scales that we're working at. Oh, I didn't mention, yeah, you can see kind of the numbers involved. So we've got almost 2,000 GPU nodes and just a little bit more than 3,000 CPU nodes. For this tutorial, we have a reservation, but that only goes up to, I think, 16 or I think 32 nodes. So you can't submit a 1,000 node job to the reservation, but you could actually, in this tutorial, go and submit a 1,000 node job and see what happens. All right, anyway, getting back to file systems. Especially for languages that like to do things like precompilation, it's really important for you to think about where all of that happens. And so I like this diagram because it kind of shows you the trade-off that any file system engineer has to deal with, right? So obviously the fastest thing that you can have is memory, and obviously you could like add layers on top of that, GPU memory versus host memory, but so this is on-node memory basically. Then you might have on-node storage. At NERSC, we have a love-hate relationship with burst buffers. So right now the burst buffer is actually just tempfs. So that just stores again to RAM, but previous systems and next systems will have dedicated high performance but very small storage for basically for bursting to for really highly latency sensitive tasks. And then Scratch is really going to be the first like classical file system that you would touch on the system that is the highest performance. That's a Lustre file system. Basically the trade-off we make is Scratch is actually relatively small. Everyone gets a huge quota, and then the way we kind of square the circle that Scratch is kind of small but everyone gets a large quota is every 6 weeks we delete your files, right? So basically the idea is if you didn't need it for 6 weeks, it's probably not that important and we're going to delete it. And then once you kind of go out of Scratch, you start to really feel the trade-off of capacity versus performance, because the community file system and the homes, actually global home and global common, they all kind of live in this bucket here. They are significantly slower than Scratch. And so if you start to run things at scale out of those file systems, you will really see it. Case in point, if you start to precompile and your Julia depot lives in home, on the logins that's okay. Once you're on the computes, you'll ask yourself, why the hell is this so damn slow? Okay, I spoke about these things already. All right, so how do you actually get onto the supercomputer, right? Most people will use SSH, so you might log into the login nodes and then use Slurm to submit jobs. So we'll be doing that in this tutorial. Now, some people will say, I don't live in the 1960s, I would like something a little bit more advanced, and so the service that we provide to address that is Jupyter. So you can log into jupyter.nersc.gov, and then you get a web interface, right? That's great. It's a little bit less weird than SSH, unless you're used to SSH. And then finally, if you're really into building workflows, especially wiring things up across sites, then we have what's called the Super Facility API, and you can read more about it at that link, but we will not be covering that here. I'm happy to answer questions. If you are interested in these sort of things, I'm happy to answer questions about Super Facility API. All right, so if you are looking at using SSH, it's very, very easy. It's very easy unless you have a Windows machine. So if you don't have a Windows machine, you basically just open a terminal and type SSH. And then you have two options. You can either type your username at sol.nersc.gov for all those people who don't like typing, or if you are if you don't mind typing and you, I don't know, you feel awkward calling Saul by his first name, you can say perlmutter.ners.gov. If you needed to run a GUI, you can use X11 forwarding, but we won't be doing that here. And so once you log in, you should see something like this. You've got the mandatory notice about don't do illegal things, and I want to stress this very seriously. Don't do illegal things on a machine that is owned by the federal government. After you got the boilerplate, you get this welcome message, and then down here you should see something that looks like your login name at Perlmutter, and then login, and then some integer. And so that means that you're currently on a login node. And from there, you can, use the rest of the system. So whenever I will be talking about Perlmutter, I mean either this or the Jupyter equivalent. I mean like you're on a login node and you're going to do something from the login node. All right, so speaking of Slurm, so the way that resources are divided amongst users, you might have seen that pie chart that I showed earlier where it shows all the different scientific domains and broken up in different slices. Well, the way that we make it so that you can actually divvy up this machine according to that pie, so we use Slurm for that. And so the two modes that you interact with Slurm are either sbatch or salloc. salloc gets you an interactive shell so that you can, so if I say go on a compute node, if you go to a compute node, you're going to be saying, well, I'm going to go salloc and then some things like down here. This would be giving you access for 5 minutes to one CPU node, right? So basically salloc, number of nodes, -c, C stands for constrained, capital C, and then you're using a CPU node, and then now you have to tell Slurm how to prioritize your job. So I'll be talking about reservations in a second, but this is one way to get resources very quickly. So if you use queue debug, and that gives you, that prioritizes your job in the queue because you're debugging something, but it limits the size and the wall time of your job. Then you say how, this is sort of shorthand notation for 5 minutes, but you could also like just put, 00:05:00, right? So you can put in a timestamp. Then finally, you have to tell what account to use. If you don't have a NERSC account already and you got one for this tutorial, you'll be on only one account, TRN 013. And by that, that's your default account. You don't have to worry about specifying this flag. But if you want multiple NERSC accounts, you have to use -a to specify what account you want to use. And then sbatch, I'll also be talking about that. That's for you've got a pre-prepared job script and you just want to submit that to the queue. Right, like your job might be very big, and if you tried in salloc to get that many nodes, you might have to wait a couple of hours. You don't want to sit around. You just sort of want to set and forget, and so that's what sbatch is for. And so later in this tutorial, we'll also be talking about using multiple nodes. And so I just wanted to illustrate how that actually works. How do you actually use multiple nodes, right? It would be kind of tedious if you had to SSH into every compute node and start something there. So we want to automate that. And the way that Slurm automates that is with srun. So when you do an sbatch or salloc, you're coming from the login node, then you're landing on a compute node, and that's actually the lowest numbered compute node in your job, and that's also called the head node. And then when you use the srun command, what srun does is it takes the command that you've just given it and it runs it once. So at that point, it depends on how you broke up your job, but like for this illustration here, it runs it once per compute node. Some, especially older HPC designs, are the head node is a separate node. It's usually some weirdo architecture that sort of lives in between the logins and the computes. But on Perlmutter and on most modern HPC systems, the head node is actually identical to a compute node. And when you do an srun, it will, whatever you're running will also run on the head node. The head node is just like a way of distinguishing a particular compute node. All right. All right, so this is how you would be interacting with a job script. By the way, if you're starting to think, wow, this is really, really old-fashioned, then I feel you. There are some ways to make that easier, but unfortunately, if you really want to use an HPC system at scale, you still have to deal with this kind of interaction, and so that's why we have to go through it. This slide is outdated. I keep wanting to update it and I keep forgetting it. All right, so, but the principles are all the same. It's just this Haswell thing. You just ignore that. You would go CPU or GPU here. But anyway, so you could create a job script. Let's call it mybatchscript.sh. And it's actually just a shell script, right? You could /run this thing and it would just run if you're already on a compute node. If you're on a logger node and you actually ran this, the srun would be like, hey, hang on, this thing here, I can't do an srun on a logger node, so then it would submit itself, and so then your script would like hang, and you might see a little message saying, hey, I've just submitted a job. But so if you notice that, that's the problem. But if you're on a compute node, you could actually just run this and it would just run. Anyway, so you would use these pound sbatch keywords at the top of your script to configure the resources that, that you would like. So basically Slurm, once you submit this to the queue, Slurm kind of looks at the top of your file. It stops reading after the first line that doesn't have an sbatch. So I think spaces are okay, but if you've got anything else other than sbatch, everything underneath it will get ignored. So please make sure that all your sbatch requests at the top. And so what you would say is, well, I'm going to use the debug queue. -n, I'm going to use 2 nodes here for 10 minutes. Haswell, yeah, well, this is from Corey still, so actually on Perlmutter this would be either CPU or GPU. -l, this is good practice, it's not mandatory. But we have something called licenses, which is just a way of telling Slurm that you're using a certain resource. Scratch likes to crash, and so if you're not using a Scratch file system, it's good just to have this bit here blank, and that way your job still continues even though your Scratch file system is crashed. And then finally you can name it. I never do that because I'm lazy. And then you would say, well, I'm going to run my Hello World program on 64 MPI ranks, or like 64 processes, and Slurm will then figure out, like, let's say I've got 2 nodes, right? So I'm going to run 32 processes on one node and 32 on the other node. And then you would just submit this, right? You can just go sbatch and then my job script, and that would submit the thing. And yeah, I just also mentioned you could also do an srlog and then just run it normally. All right. How do we actually get onto NERSC? Quick question here. Who signed up to the NERSC accounts? Please raise your hand. All right. Please keep your hand up if you actually logged into NERSC. Okay. All right. So some of you might realize that, oh, I can't log in because I haven't set up MFA yet and things like that. So unfortunately, you're going to have to do that now before you can log in. But everyone who's had their hand up first, you are all on TRN 013, and folks that kept their hand up, you know, everything works, and we might have to, for the rest, figure out if there's any problems. And to use Julia at NERSC, it's dead simple. You just go modulo Julia once you're on a login node, and then you've got Julia module. So then you can just run Julia. Another quick, one moment. Sorry. So people online can hear.
Sorry, this is a really simple question that I've struggled with. I work with a lot of graduate students that use Julia on like local clusters. Do you run into issues using a single global Julia module, I tend to just like recommend my graduate students set up Julia just in their own Scratch directory so that they can have their own versions of installed packages and there aren't conflicts between different people running different versions of packages. So I was wondering what your take on this was.
That's actually, maybe we can have a floating mic. Yeah, that's a really great question. It used to keep me up at night. I went through several iterations. I want to plug Sam's repo to HPC. That sort of makes what you've described much easier. One thing that I really hate doing, and sometimes I see that, is like someone's got like a doc somewhere, and it's like got the magic, like the 10 magic commands that you got to run every like couple of weeks to make your thing work again. That sort of automates that. So if you want to manage your own Julia, take a look at this. To do a centrally managed Julia install, I really want to. I have to show you this. Okay, this is how we do it at NERSC. This is a diagram that shows what happens. So at the bottom here you have got the system, right? You've got like CUDA, MPI, blah, everything. And that then has to all be fed into, like Julia has to somehow know how to find MPI, how to find CUDA, and so on. Now, a centrally managed Julia depot is a really, really bad idea because, you know, what happens when you know, different users have different compatibility requirements, and you know, like at some point you get some combinatorial explosion. So what we do is we configure a Julia module, which is this thing up here, that just detects your local settings, and then if you want to do, you know, install MPI, for example, you would install it locally in your user environment, but it would detect the system settings. And then also, because Julia doesn't want to live on a shared file system where it doesn't have write permissions, we have this wrapper here. At some point I will try and upstream that, and I'll have to find some people to talk to here. That all it does really is, it's like a slightly different build of Julia up that does two things. It can live in a shared environment, and it generates module files. So then you can go, you know, I want to have this version of Julia. So you can use Julia up HPC, add, I don't know, 1.12, and it'll create a module file that then you just load, and that module file will pick up all of these NERSC-specific settings. Anyway, that's a long-winded way of saying it's actually a really complicated thing to do. We're trying to make it easier, but it's not a trivial task. All right. I'm actually getting close to the end here, and then, all right, so, and then, oh yeah, so this is what I mentioned earlier. We've got reservation, I want to point out, I didn't say this here, but now we have JuliaCon 1 as the reservation, and then after lunch we have another reservation called JuliaCon 2. And so these are examples here of job scripts. You can maybe take a photo or something if you want to refer to this later. And I'll pull up the slide again if people have questions. And so the idea is basically you're going to use sbatch or salloc, and then these are the sort of flags you would use. And I would just want to point out, like, yeah, we're going to use TRN013. We're going to use GPU nodes. The reservation isn't for CPU nodes. You know, it's an HPC tutorial. Why would you care about CPU nodes? And then all these other flags you can play around with. So, for example, this grabs one node, one GPU, and it actually shares the node with other jobs. Okay, and then if you use regular, then you don't share the node with anyone. Actually, for most of the stuff we're going to be doing, we'll be using regular. I was actually trying some of Sam's work, and I think we're going to max out on GPU memory if we did anything shared. Yeah, anyway. Okay. I pointed this out earlier, so in case you had missed the QR code, here's a chance to look at it again. If you want bonus points, you're going to set your Julia depot path to something like $scratch depot. So on NERSC, $scratch just goes to the Scratch file system. So that's what this question was really about. Just put it on Scratch and be done with it. And if you did any sort of scaling runs, ideally you'd use like something like a Docker image. But if you don't have an image ready already, then just put things on Scratch. Another pro tip is before you submit your job script, run have like some small scale run of your Julia program so that it precompiles everything on the login node. Because again, on the computes, okay, Scratch ain't so bad, but still on the computes, when you now have like dozens of things precompiling at the same time to the same depot, things are going to conflict and it's just going to be a pain in the ass. It probably still works, it just delays things. All right. And actually for most of the demos I'll be using, and I think Sam and others will be using Jupyter. So you can go to jupyter.ners.gov and then you would see a screen. Mine is a bit more busy, but I can't impersonate other users, so I can't really show what it looks like for other users. But you should see like one line here called Perlmutter, and you're going to be working on Perlmutter. And so if you're already running something on one of these node types, you'll see a little stop button and a server button, otherwise you'll see start button. And you would just go and click start or server. For now, like for some of the simple stuff, you can use the shared GPU node or the logger node, but then later we'll be using exclusive GPU nodes and configurable jobs. And like if you click on any of these buttons, you first see a loading bar. You can expand the event log to see what's going on. Like it takes maybe a minute or two, and then you get yourself a Jupyter instance. And so if you wanted to use the terminal, or when like you might have already SSH'd into the system, but if you don't have SSH on your computer, you can at that point just click on the blue plus sign and then on terminal, and that will get you the terminal on a logger node, like so. And then from there you can issue any sort of terminal commands that I've talked about. Another tip is once you've cloned the repo, and then you can just I forgot to put this here, but you can go @_dir__ and from the repo, and then you can run package instantiate, and that will download all the dependencies that some of these exercises need. And then finally, if you actually on HPC systems, I really recommend sanity checks. So I recommend that you run the version info and so the version info function in mpi.jl and cuda.jl. And so the things to look out for, so on NERSC you will see cray ampage. If you see that, then everything's okay. If you don't see cray ampage, something's gone really wrong. And so probably we might need to debug that. Same, you want to, it'll be 12.4 now, but you want to see for CUDA 12.4 and then local installation, not artifact. If you see artifact here, that's also bad. All right, and yeah, before I talk about PSC and hand things over, I also want to point out to use multiple nodes from Jupyter. You can use the configurable job mode, and then you can select over here your account, your reservation, the time. So something like this will work. So you'll go TRN 013, JuliaCon 1, so that would work now. Make sure the time limit actually fits the time limit of the reservation. So the first reservation will end during lunch, and then the next reservation will go until the end of the day. And then you can click start, and that'll get you Jupyter, but on a dedicated compute node that you've just configured there. And yeah, you can start to configure fun stuff like this, right? Like you can have how many nodes, how many tasks per node, and so on. All right, on Bridges 2 on PSC, so if you signed up for a PSC account, you can go to ondemand.bridges2.psc.edu, and you should see various combinations here. There you would go and select the Jupyter Lab option, and then you have to say well, you have to specify the n tasks per node and the GPU's flags, so the extra Slurm args. Now these can be different. There's some. I know there's 8 GPUs per node, so this is me just asking for a node. But you can like fiddle with these two, and then you will see something like this. And then once it's done, once it's ready, it'll turn green, and then you can click on the Connect to Jupyter button. Now on Bridges, we haven't yet made put the kernel into production. So the GitHub repo has an installer, and that installer creates a Julia single-threaded and Julia multi-threaded tutorial kernel. And if you clicked on those, then you would get yeah, then you would get your Jupyter instance. All right, so I think that's everything from me for now. If I just go back to the overview. All right, so next we have some folks talking about PSC and JuliaHub. We're a little bit over time, but I hope that's okay. Oh yes, TJ, please. Yeah, if you would. That also gives me a chance to recover my voice a bit. We've put in a lot of buffer. Oh yeah, in the meantime, are there any questions?
How are you? Oh yeah, there it is.
No questions. But I'll be around for questions, and I'll be back after the break.
Great. And can I have a show of hands, just how many of you are set up to use PSC for this tutorial? Okay, a few. And you've logged into the system before? All right. So yeah, I'm TJ. I work in user support. If you've submitted a ticket to us in the last 6 years, you've probably dealt with me. I'm just going to give you guys a brief overview. So yeah, we have a reservation for this. It's going to be 10 GPU nodes, full nodes. So as Johannes said, you may just want to take the full node for this tutorial since there aren't so many of you, so you don't run into any memory issues. Yeah, we also use Slurm as our workload manager. He gave you a nice tutorial on a lot of those things. A lot of those things will apply to Bridges 2 as well. There will be a few different options. So these are the just some information about the GPU nodes that we have for this tutorial. 32 gigabytes of GPU RAM. Each one there's about 40 cores on each node. There's the regular RAM, 512 gigabytes. There is a local node storage that is very fast, but it will get wiped after every job, so you do have to make sure that you copy your data back to your persistent storage, which is handled by the environment variable project, and it'll result to this path here. This is your training grant for this tutorial. And I'm sorry, that is a Lustre file system, so it is a little slower if you do plan on running all of your jobs within Ocean here. Just be aware of that. You do have a home directory, which is about 25 gigabytes. So if you haven't logged in, this is just some basic information on where you can find your username within your Access account. There's also a welcome message you would have received in your email. You set your password here. There's some basic connection info in our user guide. There will also be some more information on file spaces. There's some example scripts as well. And you could find a link to that just on our main website, psc.edu. Here's just the basic SSH command. And as Johannes mentioned, the Jupyter notebook setup takes a little bit more setup on your end, but you can access that through ondemand.bridges2.psc.edu. I don't know what kind of data you guys are going to be working with for the tutorial, but if you do want to transfer anything, you will want to target the data transfer nodes here at this host name. We recently had to disable SFTP on our login nodes because it was causing some issues, just with a lot of users trying to transfer things. So yeah, we have a wrapper for salloc. We call it interact. This is a basic command if you wanted to just start an interactive GPU session using our reservation here, adjust the time limit as needed, and to put some of these new Julia builds into your environment, you would just want to run these two commands. If you were running this in an SBatch script, you would put both of these module commands in there as well before you run Julia. And just to make sure you're getting the right Julia once you load it, maybe do a which Julia, and you should see a path similar to this. We did have some older Julia builds that we used with SPAC, so if you're seeing a path that involves SPAC here, make sure you're using another one. And yeah, if you have any help, just email help@psc.edu. Maybe put JuliaCon in the subject, and I'll make sure that I get to it as soon as possible. Any questions on the PSC end?
Hi everyone, thank you for having Julia Hub be part of this HPC workshop. We are delighted to contribute a few credits for your usage today as you go through the materials with Johannes and the rest of the team. So just as a quick show of hands, has anybody used Julia Hub at all before? So, yeah, okay, I'll say thank you. So, the first thing to know is this is the code to access Julia Hub itself. So, Johannes should have sent this code around to everyone. If not, it's here on the screen, and some of you may have taken a picture. It's a long URL, but if you enter this URL, you should automatically be prompted to create a Julia Hub account if you don't have one already. And what this code should do is to give you $120 of credit. So to show you a little bit of what that looks like, I'm now logged into Julia Hub here, as you can see. But if I went to my payments, I'll be able to see $120 USD in credits here. So that's what it's going to show you. So with that out of the way, Julia Hub is a cloud-based platform, as Johannes alluded to. It serves sort of two purposes. It gives you Julia productivity tools as a first step. So it gives you things like Pluto notebooks that are dated to the platform, so you can create a Pluto notebook on Julia Hub and share it with anybody else in the world, and obviously gate it at various levels of access controls. So you can see already there are quite a few public notebooks that people have shared with the rest of the world, and you can go through them, go through some of them, open up some of them, and we have some standard notebooks here, from prior conferences and tutorials on how to do various things, physics-based simulations, control systems, and so on. So I would highly recommend checking out the standard notebooks, especially the ones that are owned or published by us. So you'll get a feel for how to use notebooks on the platform. The second productivity tool is called projects. So projects are an encapsulated Git repository. So I can, for example, go and I can import I can create a new project on Julia Hub from scratch, which will initialize a Git repository on Julia Hub, or I can import a project and give it a GitHub URL, and Julia Hub will then prompt you to authenticate to GitHub, and then we'll be able to pull the contents of your repository into Julia Hub itself. So this is sort of a nice way you can work with Git repositories in sort of a Julia native environment. And why might you want to do that? As I mentioned earlier, you have access controls for these things. So if you're in a large enterprise and you want to gate different projects and provide different levels of access controls, as some of our customers want to do, this is exactly how you would do it using Julia Hub. So this is one part of it. So this is all of the developer features we provide. We also have this new thing called on the platform called Ask AI, where you can ask it for give me some Julia code. to, I don't know, to compute a matrix inverse, and it's going to give you some Julia code over here. So we've done a little bit of fine tuning, and it'll print out some Julia code for you. What else? So this is sort of stuff you've seen from maybe even. I mean, this is essentially calling through one of the standard LLM products, right? So this is going to give you these. It's going to give you some Julia code and give you an explanation for how it works and so on. And the final piece, which is probably the most interesting to this workshop, is the jobs interface. So Julia Hub is essentially tries to be a cluster on demand. So what do I mean by that? I can go into Julia Hub over here, and if you can see my Julia environment here, maybe I'll make that slightly bigger. I have a couple of files which I've set up. It's called pi.jl and gpu.jl. What you can do with this is you can go to the Julia Hub extension, and you can launch any script from that you're developing or actively working on, and have it run on, I can have it run on single node, you can have it run multi-node, you can have it create results, you can track the process, you can track the say logging from the process, you can monitor any results from the job, and so on and so forth. So really it's sort of a cluster manager on demand, which is what Julia Hub is trying to be. So in this particular case, I have a sort of very simple script, just throwing darts on a circle and computing pi in some sense, right? By computing the area of the circle. But what's interesting about this is I'm using the Julia package distributed.jl and providing a distributed for loop, which is sort of very standard implementation, as you can see here. But now I can then go to Julia Hub, which is an extension that is enabled by default. And by the way, to get to this IDE, you would have to go to Home and then click and then launch this app called Julia IDE, and it should spawn up a new machine with the Julia IDE loaded. So Julia is natively installed in that machine, and you can just connect to it, and it'll open up a new tab with this IDE or this VS Code interface. Now, once you have this particular script that you've written out, you can then go to your Julia Hub extension, provide of course the location of the script, the bundle directory, and then you can tell it what type of machine to run it on. So for example, I could tell it to run on the smallest possible machine because I'm barely doing any compute. But I can then run it either on single process or distributed, where I can say I can run 10 nodes, right? So I can spin up 10 machines in advance to run my job, and of course everything will using the Julia distributed.jl interface. It'll distribute this work accordingly, and of course you can either have a fixed or elastic work pool. If you're interested in what the elastic is, we can speak after. We can speak obviously outside the conference. But this is exactly what this is doing, right? So 10 processes will be deployed on one master node in this particular case. But if I change this up to say 2, I can then have 20 distributed processes that will be deployed on one master node and 9 worker nodes, as you can see over here. So let me try and change this up a bit and show you how this changes. So I can make this 5 and make this 2, and then if you scroll down, you'll see exactly what's going to happen. So 10 processes in total, so 5 times 2, and you have 1 master node and 4 worker nodes. So this is how you can sort of distribute jobs in different ways using the Julia Hub extension. And of course, you could give it a time limit, because of course these jobs cost money, and you can give it several options. So we have both a Julia option as well as a Dyad option. And Dyad is our modeling and simulation product. If you're interested in that, we have a booth outside, and we can tell you all about it. to essentially do model-based design and model-based engineering and build control systems and things like that. But once you specified all of these jobs, you can then hit start, and then you can go to your jobs tab here, and your jobs tab is split into three subcategories. So active jobs, completed jobs, and time capsules. So if you go into my completed jobs, you'll see a bunch of jobs that I tried in advance. So I can open up one of them and show you, and you'll see that it'll essentially give you the inputs and the outputs of the jobs, the environment variables you use to create the job, and as well as some outputs. So I created a text file as part of this, and the text file is available for download as part of the job. And of course, if you're generating a ton of data, you can create a JuliaHub data set, which you can then upload as part of the job as well. So it does a lot of neat, interesting HPC type stuff. You can even monitor, of course, the CPU utilization of the job as well, or look at logs if the job's failed and so on. And similarly, you can use the same job interface to run things on a GPU as well. And the way to do that is to then choose from this drop down here and choose a GPU node. So I could, for example, go to this GPU script and then just have it run a simple GPU code and launch it on a GPU script from here. Note that I'm running this IDE on a CPU machine, but I'm spawning off essentially an asynchronous job that's running on a GPU machine, which will then be spawned. So this is sort of a rough overview of how you might use JuliaHub for this particular workshop. Are there any questions? I mean, really, we're sort of doing two things: there's developer stuff as well as HPC stuff. Any questions so far? If not, I will be around the conference, and if you have any trouble or any, yeah, go for it. Sorry.
Sorry, just on the Ask AI section, is this fine-tuned for Julia? I mean, like a lot of the LLMs don't do a very good job at Julia questions. Yeah,
so we've made it's going to perform a little bit better than if you just use the standard LLMs, right? Just ask the standard LLMs to generate Julia code. We've done a little bit of work before putting it up, right? So it's not just a pure wrapper. We've done some RAG and all of that stuff. As we package the application up onto JuliaHub.com. So it's going to do a little bit better. Any others? Yeah, if not, let us know, and I'll be right around the conference. So let me know if you have any questions or if there's anything else I can help with. Thanks.
Alrighty. So I'm going to do a pretty brief, since I don't want to take too much time from the more advanced content later. I'm going to do a pretty brief sort of introduction to shared memory parallelism. So that's, multi-threading, as a lot of people call it. And then I will also do a sort of overview of how the GPU ecosystem works in Julia and sort of the concepts behind GPU execution before I hand things off to Sam. The first thing that you should probably do is head to jupyter.nersc.gov if you're on NERSC. If you're on PSC, we already talked about how to set up on PSC, and then JuliaHub, if you're using JuliaHub, you shouldn't necessarily have to do this part that I'm about to show. But I'm going to start a login node job real quick just to make something easier on us later. It'll take a second to start up. So when you're precompiling stuff on most, when you're using Julia on most HPC center supercomputers, you'll typically have login nodes that have a fairly fast connection to the internet, and then you'll have compute nodes which are not typically as well connected. That's true on Perlmutter, at least, as I understand it. And access to the file system, I think, is also a little bit different sometimes. So what that typically means is that we want to precompile things on our login nodes. So if you're on the login node, you can start a terminal by scrolling down. So your notebook screen, your Jupyter Lab screen probably looks a little bit different than mine, but scroll down and you should be able to find a terminal. I'm going to do module load Julia to be sure I have Julia in my local environment here. And then I'm going to get into the, the folder for this project that we're using, the Julia HPC tutorial, JuliaCon 2025. Just be sure you're in there. And that's sort of the GitHub repo that Johannes showed earlier. You can find it here in case you haven't done that already. So I'm just going to, precompile things. You've probably done this before if you're in this room, but I'm just going to call instantiate right here and be sure that things are ready for me on the compute nodes. Hopefully this doesn't do anything because it'll take a while if it does. But looks like it's doing something. Okay, no, it's not. All right, so we can go ahead and exit this. I think I'm going to, I don't remember how to stop the servers here, but I'm going to go back to the jupyter.nersc.gov dashboard and click stop on my login node. Is there an easier way to do that from within the notebook, Johannes? To stop the server? No. So just go to the dashboard. Okay, yeah. So just go to the dashboard and stop the login job just so we're taking care of our commons here. So I have started an exclusive GPU node. I think that's what Sam will be using as well. Is that right? Yeah, so we'll be using a GPU node. It's easier. I won't be doing much, having you run much code on the GPU. We might do a little bit towards the end of my segment, but we will be using the CPU side of things. So if you go into the folder and you click on parts and then multi-threading, there's a single notebook in there called threading.ipnb or ipynb. And we're just going to go briefly over what shared memory parallelism looks like in Julia. Zoom in here. All right, so you should have done instantiate already on the login node, so you don't really need to do that again, but you can if you want it. It shouldn't do anything. So let's take a look at what the system looks like. We have, EPYC 64-core processors, and I believe each of the GPU nodes has one. Is that correct?
Yes.
Yeah.
Each GPU node has one CPU.
Each GPU node has one CPU. Yeah, yeah. Whereas the CPU nodes, I think, are two CPUs per or packages per board. So I think I'm using a 128 thread notebook here, but you should probably be using up here in the top right. You'll see that there's different kernels. Why can I not? Okay, there we go. I would go ahead and use the 8-thread version if you have it. It should say NERSC Julia 1.11 somewhere here. You may have, I think it's just 1 and 8 thread, right, installed by default. I have more because there's a way to set up larger numbers of threads, so I'll be doing 128 threads on this notebook, but 8 threads is perfectly fine for you to demonstrate as well. So we can use the HW lock library to look at some of our topology. We have one machine with 2 packages, and so on down the list, and you can see that there are some tools that let you show a graphic of what the sort of topology of your machine looks like. But I think Johannes will maybe talk or did talk a little bit about accessing the right network interface and stuff like that on being sure you're using the right network interface and topology issues like that. So yeah, we're going to look at threads. I'm sure a lot of you have already seen threads before, pretty simple. And we'll start with spawn. So Julia is task-based. We use tasks as a sort of basic parallel primitive. Sort of the most basic bit of parallelism you can extract from Julia. And everybody always starts with Fibonacci, right? So we have basic Fibonacci function, and rather than just calling fib with sort of the A and B, we can spawn a task for A and B and fetch it. And we can do that, and we can get the results pretty easily. This is going to, this is a new node, sorry. Let's see here, I can just do this from here. So spawn creates a new task. It closes over things if it needs to, and you need to call fetch in order to get the results. Parallel for loops are a higher level interface. I think they predate the task-based system, but they use it internally these days. So we can import threads, and we have parallel for loops pretty easily. We just prefix every for loop with an @threads. And by default, that uses the dynamic scheduler on the threads system. So we have 3 different schedulers built into the threads macro. The first is dynamic, so it'll chunk up the iteration space. A lot of people that are experts in the Julia community think that this for loop up here, what it actually does is it creates one task for every item in the list. That is not true. By default, it chunks up the iteration space so that you have sort of quote-unquote ideal load balancing. You have some alternatives here. You can do greedy, which is 1 task per thread, and you might have sort of unequal workloads, and I believe it chunks things up as a channel. So it takes items from this channel and runs them on each task. And then static is sort of how things used to work, I think, in the threading ecosystem, and that's an equal division of the iteration space. And the important thing about the static scheduler is that it can't be nested. So the @spawn and @threads by default are dynamic. They can be nested, so you can have multiple levels of parallelism, but the static scheduler doesn't support that. So you can see here I used thread ID just to fill each value in A with the thread ID that's running the task that is processing that chunk. And you can see I get up to 128 here, I think, or maybe even higher. Do I? Yeah, no, just 128. It's important that you not typically use thread ID. I'm sure some of you are aware of this, but the way that tasks work is that in the Julia ecosystem, tasks are not sticky. So if I start a task, it doesn't necessarily stay on the same OS thread that it started on. And so that means that during the execution of a task, your thread ID can change. So for instance, a task might be suspended while we do garbage collection or something like that, and then it might be restarted on another thread. And that means if, for instance, you're saying you're processing a chunk, an array, by thread ID, you might grab something by thread ID. If I might have the 150th thread, and I take a value from an array, and I process it by thread ID, and then I try to put it back, my thread ID might be totally different, and so I can get race conditions and unexpected results and stuff like that. All right, so yeah, this is how you call Julia with the greedy scheduler, and I can replace this with static. I think those are the only 3 schedulers right now. There might be other ones in the future. All right, so the threads interface is pretty nice if you're just doing sort of embarrassingly parallel stuff. So if you're just processing things in a loop, it works just fine. But if you need to do things like reductions, that's where things quickly get difficult and really easy to mess up. So if you have a sum, you can get quite bad results and sort of, how do I just keep executing the same thing? Oops, come back. You can get quite bad results if you do a naive reduction. And you'll get sort of different results each time, and that's because the threads are not cooperating on this reduction here. You can get race conditions, you can get corruption, all sorts of issues. And there's a couple of different ways to solve that, but largely speaking, we don't want the user to have to deal with things like locking atomics and stuff like that, the ways that we typically solve these things. We want to have a higher level interface that is easier to use. And we have those things in a couple different places. Many people have tried to tackle this problem, but one of those is OMyThreads, which I believe was developed by Mason Protter, a prolific member of the Julia ecosystem or community. And so we have functions like map, reduce, and map reduce in the Julia world. And in OMyThreads, we have the equivalent functions just prefixed with T. And so it's like threaded map, threaded reduce, threaded map reduce, and threaded for each. So tmap, treduce, that kind of stuff. And these are pretty lightweight, so the package is relatively small. And they make things pretty simple on the user here. So we can do using OMyThreads. Hopefully everything is here. And yeah, so as expected, this is just with the thread ID version, and we're just using a sort of anonymous function here. That's not surprising, but what these things help with are especially the treduce and tmap reduce, so you don't have to deal with locking and atomics and things like that for your reductions. And we can benchmark things here. Let's see. Yeah, so how much time do I have left? Oh, I'm moving kind of quick. All right, so these examples are taken both from some notebooks by a colleague, Valentin Stravi, and also from the docs for Oh My Threads. But we can do a simple summation, and we get a certain benchmark here. We'll run those. And you'll notice from the beginning that sum is quite a bit faster than our simple sum, hopefully, unless something has changed. And can be a couple different reasons for that, but Julia's sum is pretty pretty well optimized, and I believe the big thing here will be SIMD. Yeah, so we're about 3 times slower. And so we might try to do a naive parallel version here with just the equivalent of what Oh My Threads is doing. So Oh My Threads internally, if you do something like a T for each or a T map, this is effectively what it's doing. We have our sums that we've chunked up across our data input, and then we're enumerating over these index chunks. So Oh My Threads is really just chunking up the index space and then handling this summation internally by writing to this temporary variable psums. That's sort of how these functions that I talked about up here end up working. But this is written out just to show you what's going on in case you're curious. So let's see, we can check that everything looks right, but what is happening here is that we end up with what we call false sharing. So we are modifying data that crosses cache lines. So when you're loading data in any programming language, you load it in these chunks called cache lines, and if your data crosses, if your sort of for loop is crossing those boundaries, you end up sort of ping-ponging back and forth between different CPU cores. They have to end up kind of coordinating with each other in order to get sort of correct results. And so we end up actually even slower than our basic simple sum, right? Because we have a lot of conflicts. So you have to be careful when you're dealing with this that you don't create false sharing. So there's some ways to deal with that. One of the first ones is that we could pad things, right? We could create a bunch of zeros on certain sides of our array and stride things so that we're not writing into the same segment. To be clear, when I said we're false sharing right here, we have psums and we are sort of writing into indices from each thread that are too close to each other. And so that's what we call false sharing. And so one solution to that is to make psums have a bunch of padding on each end so that we fit into the cache lines and each task is writing into its own cache line segment. And you can see we're quite a lot faster. All of a sudden, let's see, we have 13 milliseconds as our minimum, and we're about 10 times faster than our naive simple sum right here, and about 3 times faster than the built-in Julia sum. You can see, of course, that the scaling is not linear. I have 128 threads, and I'm only getting about 10 times speed up in the ideal case with the padding. So our next option is to do task local parallelism, where we are, let me just run these so that I'm not ahead of myself here. Does that work? Yeah. So rather than each time we create a sum, writing it into the array, we can sort of chunk things up internally and have a task local accumulator, and we can chunk things up into that, and then once per task we can write into psums, rather than sort of thrashing our psums array and doing even more ping-ponging. So this reduces that by quite a bit, and you can see we are pretty close to the padding here in terms of speed. Let's see. And then one thing we can also do is we can use Julia's built-in sum, which we knew was faster than just the basic naive for loop that we had earlier. And we can get a little bit faster, I think, in some cases, right? Because Julia's built-in sum is quite well optimized. Let me see, and then And then finally, we can just use basic OMI threads. That's what I recommend you do each time. It's just sort of important to show you kind of what's going on internally. And OMI threads should, with this T-reduce, get about the exact same performance as we would see with this task local sum version. So that's basic multi-threading. I don't think we'll be doing a ton of that in the rest of the workshop, but of course you don't want to be wasting your CPU cores if you can. But I think we spend most of our time for the rest of the day on the GPU. So let me see. And I'm happy to go into more depth with people on threading and things like that if you'd like during the rest of the conference. You can just find me or honestly Mason or some other people to talk about that. Let's see. So I also want to give a brief sort of overview of how things work in the GPU world. So I'll just do presentation mode here. Oh, no, I won't. So most of the compute on NERSC Perlmutter is actually in the GPUs. Almost all of the performance that we get out of sort of the high performance benchmarks, things like LinPack, where we measure the sort of maximum speed of a machine, almost all of that is found in the GPU. And so we want to be able to harness that as much as we can. And unlike a GPU is kind of many thousands of very, very lightweight threads. So on a CPU, you have these heavyweight cores that can run anything that a CPU could possibly want to run. On a GPU, each thread can do only a fairly limited number of things, right? They're very good at math, but they can't, do a lot of dynamic things that CPUs can do. So here's what a CPU die looks like. We have, this one has 6 cores, and then there's a lot of other things that are on a CPU die, things like an integrated GPU. And there's an interconnect and different layers of the memory hierarchy that you can also see here. A GPU looks very different. Each one of these, they call them different things on different GPU manufacturers, but essentially each one of these little segments here you can think of as a thread. Each one of these tiny little dots on here, and they are all organized into chunks. We might call them blocks. You can call them other things like, let me see, I think warp is equivalent to block. So I can actually talk about that real quick. Later in the day, we're going to be using this, this library called kernel abstractions. When Sam is teaching, he's going to be using just CUDA itself. So on GPUs, we divide these threads up into different sort of hierarchies. The lowest level one is called a block. On other GPU manufacturers, it might be called a work group, and that's what kernel abstractions calls it because it's kind of the more common one outside of the NVIDIA world. And those are a block or a work group is a group of threads that does exactly the same thing, right? So the big deal in GPU programming is that you might have a block or a work group of 32, 64, I don't actually know the number of threads, and they can't diverge, right? They can't do different things. If you have an if statement, for instance, and one side of that if statement goes and does a bunch of sine functions, and the other side goes and does a bunch of additions or basic arithmetic, you have essentially diverged there, and you lose most of your parallelism because you have to synchronize frequently. So work groups, it was 256 is the size of the work group, apologies. And then we divide these work groups up into larger blocks, and that's how coordination is typically done. So one of the other important things that we should talk about is that when you're running code on a GPU, there's a pretty big bottleneck between your CPU and your GPU. When you're running multi-threaded or parallel code on a CPU, the interconnect between CPU cores is very fast. It's coherent. When you are running things on a GPU, you should kind of think of it as sending a message to the GPU, hey, I want you to run something, and then eventually you should wait back for the result. They're asynchronous. So your host, your CPU, will launch some work, and then it can continue doing something else, and it probably should for maximum performance. me see here. All right. So I want to talk briefly about the ecosystem so that you have an idea of how things work. So in the Julia world, the most basic part of the GPU ecosystem is GPU compiler and GPU arrays. GPU compiler is how we sort of compile Julia code down into specialized code for CUDA, Intel GPUs, AMD GPUs, even specialty accelerators like the graph core IPUs. We use GPU compiler to do that. GPU arrays is kind of the back-end abstraction for basic array work on a GPU. So just like you have broadcasting and matrix multiplication on a CPU, we have that on GPUs as well. And that's typically that's typically done through GPU arrays. And then there are some helper libraries like adapt. So if you have complex structs on a CPU, arrays that are a symmetric array of a matrix, the wrapper types from linear algebra or a transpose, you use adapt to sort of cross the boundary between CPU and GPU. That's a lot easier than converting things by hand, and it works across the different vendor libraries. And then we have the vendor-specific libraries. So Sam will be using CUDA.jl. It will work on Perlmutter. It'll work on the PSC machine bridges. I think it'll also work on JuliaHub. I think they use V100s or something like that as their GPUs. We also have AMD GPU, One API, and Metal. If you're on a Mac and you want to run things locally, you should be using Metal to use your sort of Apple GPU. And One API is for the modern Intel GPUs. And then something we'll talk about this afternoon once we're done with the most of the high performance CUDA stuff is we'll talk about kernel abstractions. So we have these different vendor specific libraries, for CUDA, for AMD, and they all work differently because the GPUs are different and there's significant differences between the manufacturers. Kernel abstraction sort of lets us paper over those things and have kernels like matrix multiplication and things like that run on all of the GPUs available in the Julia ecosystem. Kernel abstractions is great. There's also a similar library out of Oak Ridge called JACC, J-A-C-C, and that is also an abstractions library or a performance portability framework. Kernel abstractions ends up looking a lot like GPU code that you would find in CUDA.jl and AMD GPU, whereas JACC looks a whole lot more like for loops. So it's very similar to Cocos if you're familiar with that from the C++ world. And those entail different trade-offs in terms of the code you're writing and sometimes the performance. So let me see here. Unlike CPU, where we write for loops in order to get parallelism, on GPU, we sort of write things in what you might think of as index notation. So we create these kernel functions, and this one is Saxby for matrix vector multiplication, or no, sorry, vector multiplication. Wait, Saxby is, I always forget the kernels. I think it's actually just addition. So instead of writing for loops, we write each kernel such that you can kind of think of the kernel as taking the indices that it operates on as arguments. There's kind of these hidden arguments, and in the case of CUDA, it looks like block index and block dimension and thread index. And so that's the hierarchy that I briefly mentioned earlier. And they have different dimensions because they're typically divided up into grids of various shapes, and that's kind of up to the user. So this entire function right here operates on a single set of indices. Rather than taking in sort of a chunk or the entire array, you take in these indices and you operate on the arrays as if you received the indices as an argument. You might think I have sort of I as a special argument to this function. And so otherwise this looks a whole lot like Julia code. We just don't need the for loop. It's kind of above the level of the kernel. And then we'll launch the kernel using the @CUDA macro. I believe the AMD GPU one is at ROCm. I don't remember exactly how you start them on AMD GPU, but it's very similar to CUDA. And same with Metal and Intel, or One API. So just to sort of disambiguate things here, here's the kernel launch, and here's our arguments, A, X, and Y. And then this stuff up in front of the argument here is how we define this set of indices, right? So we have a block, and essentially we're defining the size of this block here. And we set the block to contain 32 threads, and we use Y as one of our indices, or one of our dimensions here, as the sort of global dimension of our iteration space. So let me see. Do I have 5 minutes left? Is that right? 5 minutes. So you can write kernels, and that's how everything is written internally. But as I mentioned with GPU arrays, you can also just use Julia's basic array notation, right? You know, you can do broadcasting, you can do matrix multiplication, you can use most of linear algebra. That's what GPUs are really good at. And if you can avoid using kernels, I highly recommend you use the high-level abstractions, right? Kernels are very finicky to tune. And they're very difficult to get correct on all platforms, right? If you're using kernel abstractions, and difficult to get high performance out of. So if you can, you want to use cuBLAS, you want to use cuSparse and things like that, because you know, tens, hundreds of millions of dollars have been poured into making those things fast. We'll get into kernel abstractions this afternoon, but I want to emphasize sort of again that GPU operations are asynchronous. So you move data to the GPU, or hopefully you don't have to move too much. You send operations, and then you wait on them to run. You don't immediately return when you call a kernel. So oftentimes, let me see, where is it? Synchronize. There should be another synchronized call here somewhere. Yeah. So you can see when we benchmark something, we're benchmarking the vector addition kernel here, and you can see we synchronize the backend at the end within the benchmark. So if you're running benchmarks and you're testing your code, be sure that you're not just benchmarking this thing right here. The reason for that is that this will return immediately. It's asynchronous, right? So VAdd will return immediately, and you'll get a benchmark, and it will tell you it took a couple nanoseconds or a couple, you know, microseconds. So if you don't synchronize, what you'll end up doing is you'll just be measuring kernel launch, and you won't get accurate results on what that ends up looking like. So I think, yeah, we have about 3 minutes left. I think that's good. I went really fast, but hopefully there's, all right. So I think up next, after a coffee break, we have Sam, who's going to talk about sort of advanced GPU programming and in CUDA. And then this afternoon, we'll get into MPI and kernel abstractions, so performance portability frameworks. Yeah. What do you have, Johannes?
I just want to make an announcement.
Okay.
All right. I think this is also a good time to synchronize about...
Synchronize.
It was not a deliberate pun. So,
Well, you made it anyway.
Yeah.
Mike.
Accidental. Oh, yeah. Anyway, so there's a coffee break upcoming. We actually accidentally skipped one of the breaks, and I do apologize. But I also wanted to make an announcement about... Okay, it's kind of... Oh, okay, I'm just being impatient. So before the coffee break, I did want to quickly announce that... excuse me, I'll just have to make my screen into like old person mode so you can actually see what's going on here. Okay. On bridges, you do need to run the installer script to make the Jupyter kernel work. There are some problems with Jupyter on bridges at the moment, so I'm just going to demonstrate this with through SSH. So if I just grab my password, and I'm going to log into bridges, and you should see in a moment there's a fancy little, okay, it tells you how many hours you have left. And so I've already gone and cloned the tutorial, And so if you'll see that there's two things in the folder here. One is the activate.sh. So if you, for example, look for Julia here, you'll see it's got like an outdated version of Julia. So what you can do is you can go source, activate, and then you can go look for Julia, and there it is. That's what we want to see. So now you can go ml load Julia, for example. All right, and to get the Jupyter kernels, just run the install.sh script. It'll just say create a multi-threaded and a single-threaded kernel for you. So those things are necessary because the Julia install on Bridges is currently in pre-production. So that's just something that I wanted to announce. If people are playing around on Bridges and it is not working, please do these two things. Yeah, so now I think there's a coffee break, and I'm around, like we're around in case there are people having trouble getting started on the different machines. And then after the coffee break, Sam will talk about GPU performance tuning. So I'll see you there. All right, so but for the time being, please grab snacks and coffee.
We will have quite some time on GPU programming. It's about HPC, right? You think why we spend maybe more time on a single node programming than multi-GPU or multi-CPU, because nowadays it's kind of more difficult, in my personal opinion, to get the good single node performance than to get the communication right. And in particular, once you have gotten the communication right with MPI, etc., it kind of doesn't change much over the years. While GPU architectures or processor architectures, they change all the time. We need to adapt. So that's why it's really a very important part in HPC.
Are you saying that getting one GPU working is so hard that nobody tries to get two GPUs working together?
No. I'm just saying that we spend a considerable amount of time on single node performance because it's something hard to do as well. It's not just to use MPI or whatever that is challenging. That was the idea. So the material here is from a course that I gave together with Tim Besar at CSCS now 2 times. So it was a 3-day course. So the material is only the one that I created for 1.5 days. So that seems now a lot maybe to you, but we will work with this material in a very particular way. I will show sometimes just the solutions and just guide you through it. And sometimes it will tell you, now try to solve this for 10 minutes or so, and then we continue. And it's not a problem if you're not able to solve it in this time, then we just look at the solution, and you can at home later still do it if you want to. All the material is completely made in a way that one can work independently. And so we have done it at CSS in the course. Also, we used this material at ETH in a master course, where they also work independently and has a hand in the exercises, etc. So it's really something you can afterwards spend some time on if you want to. Yeah, with that I get started. So Raye has already given you an introduction to GPUs and GPU programming in general. So here I just want to highlight once again that when we want to program GPUs with kernels, that we need to understand this way that blocks of threads are organized in a so-called grid. Here we only use now the CUDA way of calling things. You have seen with Raye, I think that there are different ways to call things with AMD GPU or kernel abstractions and so on. And so the key is that we want to, when we have, for example, an array in memory, and unfortunately it's a bit too, should make it bigger, sorry. To make full screen, F11 does not work, no. Can somebody tell me how to do that?
Was that Windows or something?
No, that's Ubuntu. Normally with F11 that should work.
It's not one of those upper right buttons, and you need a square.
Well, like that, we can see now. All right, sorry for that. So you see on the top an array in memory, and we have here a Cartesian grid. Ix, Iy show the 2 dimensions, give the indexes for the 2 dimensions, and below we have how we map the threads of the blocks onto this array. And you see in yellow there, this block, how this maps to the array on the top, and in red you see the actual thread, how it maps. And then at the bottom here, you can see that these block and thread, that they can be indexed in a way that you use a bit these things here, and then afterwards you get out of that Ix and Iy. Raye has already shown that a little bit, but that's really fundamental, that if you're not sure how things should look like, you can go back to this picture and look at it. And then afterwards, you can create a kernel like that. This is a memory copy kernel. You have seen that already with Raye. Now, in this first notebook, we want to look at what is really the important thing about performance nowadays. And the key here is that we have an imbalance between the speed with how fast we can compute, and the speed with how fast we can read or write to the memory. And then you can, like you see here in this ratio, compute this for a particular hardware, how the imbalance is. And so, for example, here you would see for floating points with 8 bytes that you can do 58 floating point operations per number accessed from memory. And so for this reason, we can very often consider that the floating point operations are kind of for free. We don't need to think about them. We need to think about how we move the data from the main memory to the processors. And this is what, when we are in this case, we call it memory bound. And many applications nowadays are memory bound instead of compute bound.
Why do you write the reason is that current GPUs, I'm just reading the paragraph there, I think this has been true forever and will be true forever. So the word current, your previous paragraph, it's just off your screen now. Just above this imbalance, if you scroll up one paragraph.
Yeah.
You wrote, the reason is that current GPUs can do it. I think it's always been true and always will be true. I don't think there's anything current about it.
Well, yeah, maybe. I don't want to talk about the future that we don't know yet. Yeah.
Well, I could tell you it was true in the past, and I think it's a good bet that it will be even more.
Yeah, exactly. The trend is going more in that direction. And that actually, these are numbers from the P100 GPU, which is 4 generations back. And so now, yeah, it will be more extreme. All right, now how do we benchmark a code? How to check like how fast it goes? We can use benchmark tools. You see here how that works. But in the end, this only works with time, right? Runtime, how much time it took to run your code. And for example, here with the BLapsed, which is also from benchmark tools, it gives you one number, which is the time, I think the minimum time, yeah, the minimum time over a sample that was taken. Okay, so we did that, right? And you see the performance is super low. We can compute here the total memory throughput, how much data we moved in total. And it's 1.8 gigabyte per second here. And we know that here I have the solution for the H100, which is the latest GPU at CCS. But we got 3.8 terabyte per second, or 3.7 more or less that we should achieve. And here, so we got only 1. So I wonder what's happening, right? So the reason is very simple. We have here a very small problem, and so that's why it's so slow. And so what we do here, we will increase the problem size and see how the performance increases. The performance is here the total memory throughput, simply. And you see we really get up to 3,600 here. And so here already we have a first like take-home message. You need to work with sufficiently large problems per GPU. You can look at here where the performance gets kind of good, and it's about half a gigabyte, right? We get to 3,000. So you should be at least in this size or bigger. Else you will not use your GPU well, no matter what you do, right? No matter what computations you do, it will not be well used. So afterwards, we show here that we can do the same with array programming, with broadcasting. The performance is a bit lower, 2,500 gigabyte per second. Then we can do the same with kernel programming, and we get here now only 26. Why? The reason is that we chose here thread, that we use only one thread. So the block has only one thread. And that is not a good way to do things, because the threads, they work in warps together. So you should at least have one whole warp, and the warp is 32 threads. And so what we do, therefore, okay, well, we use now 32 threads. And we look how that affects the performance. And it's much, much better, but still not good, right? 800 versus 3,700 is not good. And so we know that we need to have more than 32 threads in order to get a good performance. So we increase also here the threads, and you see that after like 128 threads, we get a good performance. And if you look at the P100 solutions, there it was with 64 threads already. And this is things that will change, right, over the years. But it's always good to know that you have these kind of limits, right? And if you don't access your data in a way that is that allows you to get good performance, then you can lose your time trying to optimize the code, and you will never get to something good. So this is the most fundamental thing: how you move your data from the global memory to the processors. Then afterwards, we do just another little thing. We keep now 32 threads in the first dimension and increase in the second dimension the number of threads. And you see that also works very well, also with about 128 threads. We get now to 3,300. And why is that interesting? It's interesting because that way we can potentially get better cache hits when we do, for example, finite differences in the y dimension, right? So when we work with neighbors in the y dimension. Yeah. Then the next important thing is that normally when you compute things, we actually read more than we write. And so here now we have a kernel that does not just read one array but two. It reads the array B and C and writes into A. And then we can see that the performance that way is yet a bit better. So we get to 3,640. That is good to know, and actually that is something that when you then add just another scalar here, then you have the famous memcopy triad, which is often used to benchmark memory throughput, to figure out the peak throughput of a processor. And you see here now we get still like the same 3,700. Of course, this is not supposed to change anything at all if you just add a scalar, right? But what matters is how much data you move, not if you do a multiplication by a scalar in addition. Okay, so that was the first notebook. I will go immediately to the second one. Now I will use the exercise notebook. You both have both notebooks, exercise and solution, immediately, such that you can afterwards immediately, for example, copy the solutions in there or run the solutions just, yeah. Okay, so now Oh, I'll put it up again.
So I recommend writing these things on whiteboards so that people could come in anytime and find those. I made that same suggestion in the other workshop.
Yeah. So it's on my GitHub, Omlins, and then afterwards GPU, Julia GPU course 2025. Has anyone gotten that? Or who has not gotten it?
The person who walks in 10 minutes has not gotten it.
Yeah.
Do we not have any whiteboard markers?
Apparently not.
None.
There's some in the other books.
Yeah, if you can, maybe that would be great. Thanks. Okay, so then let's start with the second notebook. So here we want to look at how we can now minimize redundant main memory transfer and understand its importance. Understand the limits of the total memory throughput metric for performance evaluation. Learn how to compute the effective throughput metric and understand its interest, and learn about GPU, array, and kernel programming on the way. So we create here like a little performance laboratory with these packages. And then we consider this diffusion 2D code, heat diffusion. And this code does define some physical parameters, some numerical parameters like the size of the arrays, then allocates a couple of arrays, initializes them, and afterwards we have a time loop where we do one iteration step that's called diffusion step. And this GIF here will automatically create a GIF using this call to create a visualization. Then now the function to compute an actual time step is still missing in order to complete the solver, and it can be written like this using GPU array programming. This is a particular way using macros such that you can get this kind of syntax here. Yeah. And now what we really want to do, we want now to benchmark this. And so, again, using the big problem size from before, from the previous notebook, so we can check there how big it was, and add it here in order to have a really, the big problem size. It should be at least 1 gigabyte or more, right?
Can you bring up the URL again?
Okay. Yeah, and so now at this point, the first task would be to solve that. So I will put up.
I'll take a picture and then I'll write.
Yeah. I will put it up for a moment, and I will leave you a few minutes time.
You can continue. I've got a picture of it.
No, but also.
Oh God.
You can look at how you would solve this exercise now. So the important thing to think about here is what you put here in order to get a lower bound of the total memory throughput. So this is one number that you need to add there. All right, I will continue. So now that you have time to look at it, so first, right, when we run this code, you can see what it does. Creates this GIF, it shows a heat diffusion. And now when we get to this first task, so what we were looking for was this number 11. Now how do we get that? So if you need to look at the code, right, and think what is the absolute minimum of data that has to be transferred when you write it like that. And important here is that in the array programming, things are not fused over multiple lines. So when we read something, this temperature here, for example, the full array, it needs to be read also in the next line again. And so we can count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I missed one because it's 11. So we have 11 full array read or writes. This is the absolute minimum that has to be moved, and we don't need any profiler to know that. Now if you would go and profile, then you could figure out that the total memory throughput is probably still a bit higher, because there will be some redundant reads over what you have already written here. Reads and writes. All right, so now we look at the performance that we got. We got 1,000 roughly gigabytes per second total memory throughput. And that's definitely not great for something so simple, right? All right, but now we know that we have had this problem here that we need to read here, for example, this temperature array here in this line and again here. Then this thing could actually be computed on the fly, this heat flux. We would not have to compute it first, store it in an array, and then read it again. You could directly basically insert this here into this. Basically substitute everything until we end up with a single line. And when we do that, we can avoid three times a factor 3 of memory access. All right, and so this is shown also here, how mathematically we would substitute it. And so we program that afterwards. So here we now have only the array T for temperature, and here for heat capacity, and a second array for temperature. Why we have a second array for temperature? Because when we read the temperature to make the finite differences, we need to write it in a different array, because if we would write in the same array, then we would read things that are being changed and get wrong results. And then we do here a swap of the pointers every iteration. And this is a pointer swap, so it doesn't cost anything. It doesn't move any data around. It doesn't copy them. And now, so after having done that, so the next task is then to create now the corresponding kernel, and I immediately show the result here because it's enough that you see that it works. You don't need to do it yourself. So what we do here is really what we noted above, basically substitute everything inside. We get one single line of a Raye programming statement. And believe it or not, well, of course you believe it because you can see it and try it. Now, by doing that, we get almost 5 times speed up compared to the previous one. This is the runtime speed up, right? Really, the time it takes to solve. And then if you compute the total memory throughput, the lower bound, we now use here the 3, not the 11 like before, right? We have 3 arrays that are accessed, temperature read and written, and the heat capacity only read. And then we see that this is a little bit better than before. That's not so important. The key is really, basically it's similar to before, but we are 5 times faster. Right? So this tells us what? It tells us the total memory throughput is really not a good way to evaluate performance. So then we go to the next task, and this now you could do yourself if you would like to have some experience in programming GPU kernel. So yeah, please try to do the task 4 yourself for a moment. We don't have so much time, right? You can afterwards do it at home, but at least to think about how we would do it now for a couple of minutes. Okay, so you had a moment to think about how to solve that. And here you can see the solution. How we compute the Ix, Iy, like you've seen before, and then write the equation like that. And really a key is here, we write now things like in a loop, basically, with indexes Ix, Iy, instead of writing like in GPU array programming things with whole arrays. And you need to get the indexes right to do these finite differences here. One thing to mention, this inbounds is something that you generally want to add once it works, because else it will not give you nice out of bounds errors. But this is very important to add it in order to improve performance. This is on TPU is very important. Now, when we check the performance of this kernel, we can see we get a really good performance, 3,500, right? We have seen before that like 3,700 is the performance achieved with a simple memory copy. So we're almost at the best that we could get. And this is out of the box. With these new GPUs, you get such great performance. With the P100, if you look afterwards in the solution there, it was significantly lower. It was maybe 350 or so. No, wait, I'm not sure now. At least in the 3D case, it is significantly lower. With the H100 in the 2D and 3D case, you get very good performance directly without doing something more. And of course, for this very simple case, this heat diffusion. Yeah? Now that we have seen that, now we want to define the effective memory throughput metric. And this is defined as follows. We take 2 times the footprint, the memory footprint of the unknown fields, du, and add the memory footprints of the known fields. So that was the heat capacity before, for example. And this is the effective memory access. And then we divide that by the runtime for one iteration simply, and that gives us the effective memory throughput. And in this metric, important, the T-peak, the peak performance of your hardware, is what gives the upper bound. You cannot get higher with this TF than the T-peak. All right, so now we want to compute the effective memory throughput for all this previous experiments that we did, in order to understand better how they relate each other, how good they were in absolute terms, right? Because before, this total memory throughput was not a good way to figure that out. And so when we do that, we compute TF for task 1, task 3, task 5, and we see here we get a very bad performance, 300 at the beginning, when we had these 11 array accesses, and then 1488 with the GPU array programming, where we fused everything in one line. And now with the kernel, almost perfect performance, almost at T-peak. And so we got a speed up of factor 5 or factor 12, which is not so important. And so we get to the end of this notebook, and so really the key to see is then we can do the ratio with the t-peak, with the last way that we computed it, so with the kernel, and we see that we are almost like at 95% of the theoretical performance that we can achieve. So there's hardly anything left to optimize here. All right, so now just so you know, if you want to solve anything with stencils, there is the package parallel stencil that we develop at CSCS, and there, using that, you could write the same, just like that. Here with second order derivatives, and here with first order derivatives. And unlike in the GPU array programming case above, where this would create 11 main memory accesses, in this case here it will optimize it down to this basically. It will not create arrays for these, it will compute them on the fly. The heat fluxes and the change of temperature in time will be computed on the fly. And that is how we would call it then. Okay. So we got 10 minutes left to get started with the next notebook, and this will now be afterwards a notebook with more exercises interesting to solve, more applied. And so we're going to look here at the function cumsum, cumulative sum. You probably know how that works, but if not, here you can see it. Just sums the things like that. You get 1, 2, 3, 4, when you do the sum, cumsum over one dimension here, or the third dimension. And so we're going to do a right cumsum in all 3 dimensions. And the memory access is interesting to see how that is very important. So we're going here to go from the memory copy, take that as a starting point, and add there the computations, and try not to lose performance doing so. So yeah, we start with a 3D memory copy kernel, and we get 3,200 gigabyte per second, so that's good enough. And then afterwards, so the first exercise here, which I will not show you right now, the first exercise is to create a so-called grid stride loop. That's a very important way, a very generic way to access data. For many problems you can use that. It means that you create, over the third dimension, you make a loop instead of accessing it all in parallel. So the first task here is to do this grid stride loop. So again, think a moment how you would do that. Starting from the memory copy kernel above. what you would need to add, how you would do it. Or what you would need to change, basically. All right, so that is very simple. To create the grid stripe loop, you just replace the IZ computation of a thread ID, you replace that with a loop. So IC is now obtained from this loop. And so it means that we have a serial access over the third dimension. And that is exactly what we need, right? In order to make a cumulative sum over the third dimension. We need to have a serial access over the third dimension. Because the cumulative sum is an inherently serial algorithm. Well, one can also in parallel optimize it a bit, we'll see later, but like the basic way to do it is to do it serially. And so we do that and we see that the performance is just as well as before. We changed now the way we access the data and performance is the same. And so we can go one step further. We should not yet look at the solutions here. So the next task is now to control registers. So we want to control the registers in order to do now the cumulative sum over this third dimension. Here, sorry, task 2. Yeah. We want to do the cumulative sum over the third dimension. Now that we have this serial access over the third dimension, we can easily do it. So think about it for a moment. So it's midday. I will show the solution after the break. So if you want, you can think about it more or try it more. Also when we come back. Because this is really something fundamental. It has access of an efficient way of accessing the memory, and then doing the computations in registers in order to get optimal performance. It's a very simple exercise, but it's something very fundamental. Yeah, so continue if you want for a moment, and see you after lunch.
I just want to do a quick poll. Who here has been using the NERSC Jupyter kernels? And they're working for you? That's so odd, because for some user accounts they are not working. I'm working on a hot fix for the problem. I was able to reproduce it, but not in every account. So it's something about how traffic is being routed from the computes to your browser, but we don't know yet what's causing it.